Okay, so today we are going to learn another technique of finding integrals, uh, the inverse substitution. In the previous lecture, we were talking about the integrals of powers of sine and cosine, or the integral of powers of secant and tangent. Well, that is because of we are going to turn many functions into sine and cosine or secant and tangent. And here's how. First, what is the inverse substitution? Well, normally the substitution is when you look at what you have and you say, okay, I will let my u to be whatever in terms of x. But inverse substitution is the other way around. We are letting x to be a function of something else. Instead of getting a function of x as the independent variable, we are writing x as a function of another variable. So we are introducing another variable. So pretty much you're assuming what you are having, the x is like the row of u, and then you rewrite it into something else in terms of another variable. Okay, so if you do that, you just go ahead and say let my x to be g of t, like here. Then each of your x's becomes g of t, and this becomes g of t, this becomes g of t. You will have this, and then for the derivative part, the derivative of g of t, you do the chain rule. The derivative of g comes out, g prime t comes out, and you have dt. By doing that, you are really changing, well, you are again changing the independent variable here. But the idea is more like not coming up with something in x, but you go ahead and say, I want my x to be whatever function, and then it will work nicely for you. In particular, the reason you are making your x to be a certain function is because, well, at least in this section, it's because you want to get rid of that radical. So for example, when I'm evaluating this integral of 1 over square root of 4 minus x squared, I would say I don't like that square root and I want that radical disappear. How can I make it disappear? So if my x is 2 sine theta, which theta is some other variable, then my 4 minus x squared will be 4 minus 4 sine squared theta, or 4 times 1 minus sine squared theta. Now when you square root it, you are taking radical of this. That will be 2 square root of 1 minus sine squared theta, which will be 2 absolute value of cosine theta. If somehow you can make x a function that is 1-to-1 in terms of theta, and also if you can make cosine x positive, it will be just 2 cosine theta. Okay, so let's assume two sine theta, x equals 2 sine theta is 1-to-1 and cosine theta is greater than 0. We are going to talk about on what range, on what choices of theta, both of them will be true. But right now, let's just assume that will happen. Then look at my original integral. This will be the integral of, again, I'm letting x to be 2 sine x. 1 minus, let me write this again, 4 minus 2 sine theta squared. The x also is 2 sine theta. We already work out this radical. This radical is 4 minus x squared, which will end up with 2 cosine theta. So this is the integral of 1 over 2 cosine theta. and differentiating this part. First you get 2, then you get cosine theta d theta. They cancel each other, and you really just get theta plus c. But what is theta? Theta is the angle such that x equals 2 sine x. So sine theta actually is x over 2, or theta is sine inverse sine of x over 2. Okay, so this is actually inverse sine of x over 2, then plus c. Well, again, assuming, we have the sine function to be 1-to-1. Remember, in general, the sine function is periodic. It's not 1-to-1 always. But you can find a particular range of theta so that x is 1-to-1. Sorry, sine theta is 1-to-1. X equals 2 sine theta. Okay, so when sine theta is 1-to-1, x is 1-to-1. And also cosine theta is positive so that you can get rid of that absolute value. Get rid of this absolute value. So here's the range of each of the functions. As I said, we do these inverse substitutions because we want to get rid of that radical, and depending on what's under the radical, you do different substitutions. But the idea is the same, you use Pythagorean identity. If you have a squared minus x squared, imagine that's a 1. You want something, this is 1. So you want something so that you get a perfect square under the radical. So when you are doing a squared minus x squared, you are going to make your x sine theta, a times sine theta, so that, under the radical, you will have 1 minus sine squared theta after you pull out the a, so you get a cosine theta. Where are we choosing it? We are choosing pretty much where you choose the inverse function. For sine, you take negative pi over 2 to pi over 2. Notice on both quadrants, cosine is positive and sine is 1-to-1. Because from this is your sine curve and you are picking this part, okay? Or you are picking the range of inverse sine. Similarly, you can do the same thing to make both the function 1-to-1 and also the absolute value that you are going to get from the radical positive. For a squared plus x squared, you are having essentially, again, 1 plus x squared. 1 plus what square of what trig function give you another perfect square? You use 1 plus tangent squared equals secant squared. So 1 plus tangent squared. Of course, you pair it with coefficient, so x will be a tangent. Similarly, if you are doing subtraction, it's like x squared. What squares minus 1 give you another perfect square. So secant squared minus 1 give you 10. Okay, so your a will be secant squared. The idea is when you plug in under the radical, you have a perfect square. That's what you are looking for. And you don't need to worry too much about these ranges. They will just end up like nicely. When we talk about the inverse functions, we did prove, remember, no matter your x is positive or negative, the two formulas end up to be the same. So that's pretty much the same reason. But you need to I would say you should have the idea why you are doing these substitutions, because these expressions all seem very similar, and if you don't know the reason behind these substitutions, you will mix them up. Okay? So pretty much what we are using is 1 minus sine squared theta equals cosine squared theta, and 1 plus tan squared give you secant squared, or secant squared minus 1 give you tan squared. Those are the formulas you are really using at the end. Another example, we want to evaluate the integral of this. So I'm having x squared plus 1 under my radical, and I want to perfect square that in that. So my x will be tan theta. When my x is tan theta, let's see what we have. 1 over, this will be tan squared theta, and the radical x squared plus 1 will be tan squared theta plus 1. This is secant. So times secant theta times d tan theta. And the derivative of tan, sorry, let me copy all these. The derivative of tan is secant squared d theta. Then we can cancel the secant with the secant, and we are having actually a secant over a tangent squared. Let's write them in terms of sine and cosine. We'll see them clearer. Tangent is sine over cosine, so its reciprocal will be cosine over sine. Square tangent means square both, times secant is 1 over cosine. So we are really having the integral of 1 over sine squared theta cosine theta d theta. You again have a integral of powers of sine and cosine, and when you have one single odd power, that's the thing you push inside the derivative, right? So this is my du. 1 over, let me write it this way, sine theta to negative 2 power, then d sine theta. Let my u to be sine theta. I'm having the integral of u negative 2 du. And that is power rule. You add exponent by 1, you flip it, you plus c. This is negative, I don't want to write negative 1 on the exponent, 1 over sine theta plus c. But in the given question, there's no theta. You made the theta up. Then you need to find what it is. How are you going to find sine theta? You have tangent theta, and you need to express tan theta. You need to express sine theta. What do? You draw a little right triangle. This is my theta. Tangent of theta is the opposite over the adjacent, so I make it a fraction. I'm saying this is x and this is 1. That's my tangent. Then Pythagorean theorem tell me this hypotenuse will be square root of 1 plus x squared. Then sine theta will be the opposite over the hypotenuse, or its reciprocal will be negative. You flip it. Square root of 1 plus x squared over x. Then you add that constant. Remember, in the given expression, there wasn't any theta. You called something theta. They didn't know. So at the end, you need to get rid of the theta, write out the trig ratios in terms of your definition, or write out the theta, the angles themselves as inverse. Okay, now you can pause the video and try practice number 1. The second example, I'm having this integral, and in particular, I'm trying to get this part a perfect square. So apparently my x will be 2 times sine theta, because I need the 4, and then I need 1 minus sine squared. Okay, then the original integral becomes 4 sine squared theta 2 sine theta squared over square root of 4 minus 4 sine squared theta d 2 sine theta. This gives me the integral 4 sine squared theta over 2 cosine theta times the derivative of 2 give me 2, derivative of sine theta give me cosine theta d theta. So the 2 cosine theta and 2 cosine theta get cancelled, and we end up with, let me pull out the 4, sine squared theta d theta. You have an even power of sine by itself. What should you do? Half angle formula. So this is 4, the integral of 2, 1 minus cosine 2 theta d theta. So that will be 4 times 1 half 2 d theta minus, well, let me do this so it's clearer. Okay, the integral of 2 cosine 2 theta d theta. I will need a 2 here to make that input of cosine theta. So meanwhile, I divide it. This will be, I'll keep it at this step, minus cosine 2 theta d2 theta. So that gives me 2 theta from my first integral minus sine 2 theta from my second integral, and then plus c. How are we going to get this sine 2 theta? Sine 2 theta, we have the double angle formula. That's actually 2 sine theta cosine theta plus c. And when you have that, sine theta cosine theta, when you have tricks of theta itself, you can find them. My x equals 2 sine theta, which means sine theta is x over 2. So here I am, opposite is x, hypotenuse is 2, then the adjacent will be 4 minus x squared, 2 squared minus x squared. And also, theta is sine inverse of x over 2, since sine theta equals x over 2. You take its inverse. Then I can put everything together. I'm having 2 times sine inverse x over 2 for my 2 theta, and then minus the 2 sine theta x over 2 cosine theta square root of 4 minus x squared over 2, and then finally plus c. I can cancel a 2 with another 2, so this will be 2 sine inverse sine of x over 2 minus x over 2 square root of 4 minus x squared, then plus c. Well, again, the given integral is in x only. Your final answer is in x only. Next example, this time instead of having square root of 4 minus x squared, I'm having x squared minus 4. So my x will be 2 secant. And the integral will be square root of 4 secant squared minus 4, or minus 1 factored out over 2 secant theta d 2 secant theta. So the radical will give me 2 tan theta over the 2 secant theta I was given as x, times the derivative of 2 is 2, the derivative of secant is secant tangent, then d theta. I cancel my secant with my secant, I cancel my 2 with my 2. I'm getting the integral of 2 tan squared theta d theta. And I don't know if you remember, we did a very similar question in the previous packet. when you have 10 squared, write it as the other way, 2 secant squared theta minus 1 d theta, where secant squared is the antiderivative, is the derivative of 10, and of course 2 d theta, you can evaluate that. So this gives me 2 10 theta minus 2 theta plus c. Then same issue, you can't leave anything in theta. Let's solve for the 10 theta and the theta, pretty much. My x equals 2 secant theta, which means secant theta equals x over 2, or flip it, cosine theta equals 2 over x. So first of all, x theta equals inverse cosine of 2 over x. You get your x, you get your theta. Now you need 10 theta. Cosine is adjacent over hypotenuse, and the third side will be hypotenuse squared minus adjacent squared. Then this will be 2 10, the opposite over adjacent, minus 2. Theta is the inverse cosine of 2 over x, and then finally plus c. The 2 and the 2 cancels each other, and you are getting just the x squared minus 4 minus twice inverse cosine of 2 over x, then plus c. And when you box it, make sure everything is in the given variable, in this case, x. The last example for this packet, well, these questions are very computational, so they are quite long. You have to be very patient and, very careful with the details. And you still might get it wrong because there are too many computations. What I care more about is that you get the idea. Okay, anyway, let's continue. This is a definite integral. I gave you the limits. Well, it's the same, but you get the limits. Actually, sometimes it's a good way because when you do the substitution, you change the limits together with the substitution. So you don't need to do, like, let me figure out what 10 theta is given that my x is sine theta kind of thing. You will get theta as the limits. You will just evaluate them. Hopefully you get theta as a nice number. Anyway, let's see. 4 minus 9x squared. So pretty much let me pull out the 4 so you can see it clearer. 1 minus 9 over 4x squared. Oh, sorry, I want to pull out 9. So I'm having 4 over 9 minus x squared dx. So I will make these 4 over 9 minus 4 over 9 sine theta squared, which means my x is actually 2/3 sine theta if you compare. X squared equals 4 over 9 sine squared theta. So x itself is 2/3 sine theta. Okay, so that's my x. Well, as I said, you have limit. When x equals 0, the 0 equals 2/3 sine theta. So sine theta also equals 0, where theta equals 0. And when x equals 2/3, 2/3 is the 2/3 sine theta. My sine theta would be 1, where theta equals pi over 2. And these are what I was talking about. Hopefully you get a nice limit or limits for your theta, new variable. Okay, now I can do the rewriting. This equals 0 becomes 0, 2/3 becomes pi over 2, over 4 minus 9 times 4 over 9 sine squared theta d 2/3 sine theta. So they cancel each other. You can pull out the 4 under the radical. So again, this is square root of 4, which is 2. Then 1 minus sine squared give you cosine theta times coefficient pull out 2/3. Derivative of sine is cosine, then d theta. So again, we end up with even power cosine squared theta d theta. And this is, 4 over 3, that should be 3. 4 over 3 from 0 to pi over 2, 1 plus cosine 2 theta over 2 d theta. So again, I'm having two terms, the 4/3 times 1/2 the integral of d theta, if you want a 1, plus the 4/3 times the 1/2, 0 to pi over 2, cosine 2 theta d, again you want, let me do it here, the 2 added to the theta, so you multiply another 1/2 outside. And this gives me, the first part gives me, well, I can cancel the 2. So I'm really having 2/3 theta from 0 to pi over 2. Then on the other side, I'm having 4 cancels with the other 2 2's. I'm having a third. Sine 2 theta evaluated from 0 to pi over 2. So the first part, I'm having 2/3 pi over 2 minus 0. The second part, I'm having a third sine 2 theta, 2 times pi over 2, pi minus sine 0. So this gives me 2/3. Well, you don't need that, that's 0. You don't need that, that's 0. You don't need that, that's 0. So the only thing survive will be 2/3 times pi over 2 or pi over 3 after you cancel the 2's. So when you are having a definite integral, as you can see, you didn't really go for the triangle to solve for the other trig ratios, because in this particular question, your angle is a special angle. When the angle is not a special angle, you would end up with something, say, instead, because you get your theta from solving, you would have something like sine inverse of, I don't know, well, 3 is not a good number, a third, something like this. When the sine ratio that you get is not a special angle, you won't have theta as a number, then you will have to use inverse sine or inverse tangent or inverse secant, which will become inverse cosine based on your substitution. Okay, now you can do the rest of the packet.